Okay, so we just talked about like the error. Okay, if we try to iteratively, do this prediction. Okay, do this forecast. Okay, then the error will get accumulated. And the result is going to be worse and worse. Okay, and so what do we do? Is there a better way to do it? Okay, we can do it like this. Okay, the second option, to train an RNN to predict all 10 next values at once. Okay, so we still use sequence to vector model, but it will output 10 values instead of 1. Okay, so we first need to change the targets to be vectors containing the next 10 value. So, so we first need to, basically prepare our data set, okay, so that the ground truth contains 10 value instead of 1 value, okay, because this option, okay, if we do this option, then the model needs to be retrained, obviously, okay. So you can see, okay, first we generate like a n-step plus 10, and then, okay, in the training set, and we split it into training set, validation set, and test set, and the ground truth will contain the last 10 value, okay, for each series, okay. So now, okay, we just need the output layer to have 10 units instead of 1. So this model is similar to the previous one, okay, except the last layer has 10 units, 10 neurons, okay, has 10 neurons. And then we can, train this model, and then each time, okay, we feed in the first 50 value, and it's going to predict the next 10 value, like, in one, inference, okay? So that's it. So this model works nicely, okay? So the MSE for the next 10 time steps, okay, is about 0.008. So this one is much better than the linear model, okay? But we can still do it better, okay? So how do we improve over this one? Okay, this one is already better than the baseline model, okay? But instead of training the model to forecast the next 10 value only at the very last time step, we can train it to forecast the next 10 value at each and every time step, okay? So we can turn this sequence to vector RNN into a sequence to sequence RNN. Okay, so what exactly are we talking about? Okay, it's like this. Instead of just getting the last output, okay, there will be many more error gradient. Okay, so this is exactly what, so far the model that we are using, okay, is more like this, because it's a sequence to vector. No matter this vector result is 1 value or 10 values, okay, basically, okay, the output is not a sequence, okay, so that is why, okay, remember I told you, okay, the gradient flow back in this case, okay, for model training is going to be worse than the sequence to sequence model, okay, so this one actually, I mean, should work better than the one that we have. I mean, let me use this one as an example. Okay, for example, okay, Let's say we want want to use the previous 50 value to get the next future 10 values. Okay, this one we just keep getting the input, and then we output the next 10 value here. But this one is like okay, say we get the first 10 value from 0 to 9. This one will output value from 10 to 19. Okay, 10 to 19. Of course, this output is useless because we know the value from 10 to 19, right? Right? Okay, suppose we have 10 RNN neurons here. We have 10 recurrent neurons here. So we get the first 10 value, and we also output the next 10 value. Okay? And the next round, okay, we are going to shift one position to the right. Okay? It's going to be x1, x2, x3, x4, x5, up to x10, right? And this one will be outputting x11, x12, x13, and so on, up to x20, right? So again, okay, in the next round, okay, in the first round, okay, you try to use the gradient to do the some update, and then in the next round you can use the gradient to do some update. So, I mean, with each sequence, okay, you have a lot of gradients to improve this model. With each I mean, what should I say? With each like training iteration, or I should say that. I mean, so basically, I mean, when this thing runs to 41, 42, sorry, 40, 41, 42, 43, 44, up to 49. This one will output 50, 51, 52, 53, up to 59, right? Those 10 numbers are what we want. Okay, but before that, we actually get a lot of input. We get a lot of like opportunity to adjust the model. Okay, so this is like something that's remember. I mean, I discussed with you like why sequence to sequence is better than sequence to vector model when it comes to predicting time series. Okay. So where are we? Okay. Okay. So after we prepare the data set, and then no, this one. Okay, this one. After we prepare data set, this one. Okay, this is like we output the next 10. This is still like a sequence to vector, but now, okay, we want to convert that model to sequence to sequence. Okay. So, okay, to be clear, at time step 0, the model will output vector containing the forecast for time step 1 to 10. Okay, then at the time step 1, so there's like some kind of overlapping. Okay, the model will forecast the step 2 to 11 and so on. Okay, so the offset is 1, it's not 10. I'm sorry. Okay, so each target must be sequence of the same length as the input sequence, containing a 10-dimensional vector at each step. Okay, so we need to prepare this one, prepare the target sequence. Okay, so we prepare this target. Okay, which is a sequence of 10-dimensional vector. Okay, and then okay. Each time, like if it's like from 0 to 9, so it's 2 to 10, and from 1 to 10 we have 11. 2 to 11, and so on. So the ground truths will be different now. Okay, so we need to prepare those ground truths. Okay, and then, okay, we need to also change the model. Okay, we also need to change the model. So at each time step, the model only knows about the past time step. Okay, it cannot look ahead. It is said to be a causal model. Okay. So after you prepare this data set, the training data set and the ground truth, okay, the target, I mean, has a lot of overlap. So this type of stuff, okay, it's okay, okay. So this is not cheating, okay. At each time step, the model only knows about the past time steps, so it cannot look ahead, okay. So the causal model, basically, like the output will contain some entries that, you know, it already has previously, okay. It's like what I just told you, this one. Okay, x0, x1, x2, x3. This one is x1, x2, x3, x4, x5. So only the x5 is unknown. From x1 to x4, okay, they already appear in the input, but that's fine. This is fine. The model with such a property is called causal model, okay? So back. Not this one. No. Too much. Where are we? Okay, here. So to turn the model into a sequence-to-sequence model, okay, we need to set return sequence to true in all recurrent layers, okay, including the last one, okay, including the last one, because the output will be compared. The whole output will be compared with the ground truth, okay, to see like if it, you know, everyone, okay, every output, I mean, I mean, it's correct or not, okay, I mean, if it's not, like, how much difference it is, I mean, it contains that, and use that to compute the gradient, and, you know, so that's the last layer, okay, the output layer is also need to set like return sequence equal to true, okay. So we must apply the output dense layer at every time stamp, okay. So Keras offer a time distributed layer, okay, for this purpose. So it wraps any layer, okay, such as dense layer, and applies it at every time step of its input sequence. So it does this efficiently, okay, reshaping the input so that each time step is treated as a separated instance, okay. So it reshapes the input from batch size, time steps, input dimension, to batch size, times time step, and input dimension, okay. So in our example, the number of input dimension is 20, okay, because previous layer, okay, the layer before the output layer has 20 neurons, right? So the input dimension is 20. Then it runs the dense layer and finally reshape the output back to sequences, okay? So it will reshape the output from batch size times time steps, output dimension, to batch size, time step, output dimension. Okay, so in our example, the number of output dimension is 10, okay, because the dense layer has 10 units, okay. So what we do is like this, okay. The first two layers pretty much stay the same, okay, but you can see the return sequences equal to true. For the second layer comes back, right? Comes back. Because now we are not connecting this one to a dense layer, okay? And instead, the last layer is going to be time distributed, okay? This time distributed, okay, conveniently, okay, accept the previous sequence and do some work, okay, kind of acting like a dense layer, but eventually it's going to output the 10 number as a sequence. Okay, so so this is like how you write a model. Okay, so the dense layer actually supports sequences as input as well. Okay, so it will handle them just like time distributed. Okay, meaning it is applied to the last input dimension only. Okay, so we could replace the last layer with just dense layer with 10 neuron. Okay, but for the sake of clarity, okay, however, we will keep using time distributed dense 10. Okay, because it makes it clear. Okay, the dense layer is applied independently at each time step, and that the model will output a sequence, not just a single vector. Okay, supposedly, like, you could use just dense layer to output the sequence as well, but it's going to be very confusing because normally the sequence, if you use like a dense layer as output layer, it normally output a vector instead of sequence. So it's better to wrap the dense layer with a time distributed, like what we are doing here. So this time distributed wrap the dense layer, okay, so that it will convert this one into a sequence. Okay, and then okay, all outputs are needed during training, but only the output at the last time step is useful for prediction and for evaluation. So although we will rely on the MSE over all the outputs for training, okay, we'll use a custom matrix for evaluation because okay, when you are doing training, all the outputs will be used for training. But for evaluation, we will only consider the last 10 output. Okay, the previous outputs, okay, they can be used for training, but not for evaluation. Okay, so so we need to write a customized metric for evaluation. Okay, to only compute the MSE over the output at the last time step. So this is like we define last time step MSE. Okay, so it's going to return matrix that means square error. Okay, y true. Okay, this is -1 means the last one, the last prediction. Okay, so we define this optimizer to be Adam, and we put the matrix. Okay, put in like our defined MSE, last time step MSE as a matrix here. Okay, the other part I think remains the same. So we can get a validation MSE of about 0.006. Okay, so this is not a small reduction. Okay, the previous one. Okay, before you convert it to the sequence to sequence, the error is 0.008. Okay, it's where is it? Here. 0.008. So now we are getting 0.006. Okay, so this reduction is 25% reduction in terms of the error. Okay, so this is quite a lot of reduction. You cannot just treat it as a 0.002 reduction. Okay, in terms of like a absolute value, it's not much, but this is actually a lot. Okay, so you can combine this approach with the first one. Okay, what do we mean by combine this one with the first one? You can predict 10 at a time, and then okay shift predict next 10 at a time. Okay, you can do the iteration. So you may wonder, why do we, say if we want to predict like a 50, let's say we want to try to use the first 50 to predict next 50. Okay, one extreme is to use 50 to predict directly predict next 50. Okay, using we can retrain a model, okay, sequence to sequence to directly predict the next 50, right? Okay, the second approach is each time we predict 10, 10 sequence. The other extremes, each time we predict one time step at a time. I mean ahead, and then we move, this window for one step, and then predict the next one. So we do this 50 times, right? Okay. So the first extreme is use the first 50 to predict next 50, one try. Okay. Next one is each time we predict one number, and we do it 50 times. Okay, I already told you, okay, the second approach is bad, right? Okay, but is the first approach better? Use the first 50 to predict next 50. There's a certain, let me put it this way, okay, the other extreme is not necessarily better, okay? Think about this, okay? Using the first, maybe using the first 50 to predict next 50 is not, you may not consider this as too much or too unreasonable. Okay, let's push this to an extreme. Let's try to, can we use the first 10 to predict next 50? You see the direction I'm going, right? Okay. One is the first 10 to predict 1, and then 1. We just shift this window. Okay. The next one is use this 10 value to predict 50 value in one inference. Okay, that's the other extreme. This extreme is not necessarily much better, right? Because you don't have enough information. Okay, or if you think about it, if you use this idea, can you train a model that use one number to predict the next 100 years? One inference. This sounds a little bit strange, right? This should make you think it's unreasonable, right? Same thing applies. Okay, if you use first 50 to predict next 50, it's not necessarily better than you use first 50 to predict maybe 10 and then shift a 10 and then predict next 10. We know iteratively doing this too much is bad, right? Okay, each time predict one value and do it too many times is bad. We know that because error gets accumulated. But the other extreme, using just this amount to predict a large amount of information, that's also not going to work that well. Okay, from the information theory point of view, okay, it's not going to work that well. If you have 50 numbers, well, maybe predict next 10 steps is probably reasonable. But if you have only 10, you want to predict next 100, it doesn't sound right, right? It doesn't sound right. So somewhere in between. So here, what we want to tell you is, it should be somewhere in between. You use first 50 to predict next 10, and then you can do this repeatedly, maybe 2-3 times. Then this allows you to predict next maybe 30, 50 timestamps. Okay, that's already a lot. Okay, you don't want to go one extreme. You don't want to go the other extreme either. Somewhere in between should be something like this. Okay, so concatenate this value to the input time series and use the model again to predict the next 10 value and so on. Okay, you can do this as many times as needed, of course, conceptually, just like you can predict one value and then shift one value and then predict next value, and you can do as many times as you want. But, okay, of course, it may not be very accurate for long-term prediction, but it may be just fine if your goal is to generate if you want to predict, if your prediction is a long-term prediction, then this approach is not going to work that well either. Okay, actually, for long-term prediction, nothing works. Okay, you can only predict to a certain extent. Okay, but I just want to tell you, okay, one extreme and the other extreme, both extremes, okay, do not work well. Somewhere in between is perhaps something you should try. But even no matter which one you do, for really long-term prediction, it will not work that well. Okay, and sometimes you can also use because this one allows you to generate a sequence, right? So sometimes we can also use RNN to do some creativity task. For example, we can use RNN to generate to compose music for us. Okay, and so it may be just fine if your goal is to generate original music or task, as we will see in chapter 6. Well, we are not going to talk about chapter 16, okay, because that's about NLP. But just want you to understand, okay, sometimes, okay, some task does not necessarily have a certain goal to meet. Okay, for example, like a creativity type of task. Okay, in that task, okay, really even if your RNN model, you use RNN model to generate long-term like a sequence. You may feel like, oh, it's going to be it contain like error, but that's fine. Okay, we are talking about creativity. No, creativity cannot be measured by error, anyway. Okay. So when forecasting time series, it's often useful to have some error bars along with your predictions. Okay. For this, an efficient technique is MC dropout. Okay. We already talked about MC dropout, right? We talked about that in chapter 11. Okay. So you can add an MC dropout layer within each memory cell. Okay. Dropping part of the input and the hidden states. So after training to forecast a new time series, use the model many times and compute the mean and the standard deviation of the predictions at each time step. So we talked about MC dropout already. So this is just to tell you, okay, how to generate an error bar with your prediction. Okay. So simple RNN can be quite good at forecasting time series or handling other kind of sequences, but they do not perform as well on long time series or sequences. Okay, there are there are several reasons for that. Okay, so the first issue, okay, to train RNN on long sequences. Okay, so we must run it over many time steps. Okay, so we are going to do unrolled through time for many time steps if it's going to be for a long sequence, right? But the issue is, okay, like any deep neural network, it may suffer from unstable gradient problem. So this is the first issue, okay? So we discussed this issue in chapter 11 and also the solution for that. But for RNN, there are other solutions available to solve this, okay? And it may take forever to train, or training may be unstable, okay? So moreover, when an RNN processes a long sequences, okay, it will gradually forget the first input in a sequence, okay? So the earlier input will eventually be forgotten, okay? Because your neuron, okay, your basic RNN neuron only keep one value as its state, right? That value, okay, is too simple to keep too much memory, to keep too much information anyway. So eventually, when you know the simple RNN cell, okay, has too many, you know, when you face like long sequences, okay, it's going to, you know, contain too much information to store using its state. So it's going to, what's going to happen eventually is going to be like the newer information that fed into the basic RNN cell will be memorized better, okay? But the older information, meaning the earlier information, will gradually be forgotten, okay? So that's the issue, right? Because you don't know, maybe like the earlier information, some of the earlier information may be important, right? May be important for certain task, okay? So what do we do? Okay, we can also, you know, we also have like solution to deal with this problem is called memory loss. This problem is called memory loss. So we also have problem. We also have solution to deal with memory loss. So first is, you know, the gradient, the unstable gradient problem. How to deal with that? The second is memory loss problem. How to deal with that? We have let's look at both of these problems, starting with unstable gradient problem. So many of the tricks that we use in deep neural networks to alleviate the unstable gradient problem, okay, of course, they also can be applied for RNN, okay? So such as good parameter initialization. Remember, we talked about He initialization, Lechon initialization. Remember, if you forget, like chapter 11 is your friend, okay? Go check it out, okay? I want to remind you guys, okay? The first, we'll have final exam, okay? It's not like we don't have final exam. We have final exam before the week before the final exam week, okay? Which is, what's that? It's January. I forget about that date again. Can you guys check? In January, we only have 2 classes, right? The second class is the final project presentation. The first class in January is the final exam. It's January, which day? January 6th. Okay, so please remember. Okay, we have a final exam. Okay, so I don't want you guys to be surprised. Okay, I mean, oh, there's a final exam. I mean, at the last minute. No. At the very beginning, I mean, when we talk, I mean, in the syllabus, I already we have one final exam, okay? And for example, like when I talk about good parameter initialization, even though this thing has been covered in a very early stage of this class, chapter 11, I want you guys to be, you know, to remember because they may appear in final exam, okay? So faster optimizer, okay, such as you know, non-adaptive ones such as momentum, next row, or like adaptive optimizer such as Adam, Naden, okay, LRMax, those type of optimizer. Dropout, okay, we talk about dropout, right? So, however, non-saturating activation functions such as ReLU may not help as much here, okay? Because in RNN, it's a little bit special. The ReLU can be used in RNN, but a lot of people, okay, find that it is not we know the ReLU helps model training for CNN, for MLP, okay? But when it comes to RNN, ReLU works, but it's not as helpful as the other type of neural networks, okay? And they may actually lead RNN to be even more unstable during training. Why? Because suppose gradient descent updates the weight in a way that increases the output slightly at the first time step, okay? Because the same weights are used at every time step, the outputs at the second time step will be slightly increased, right? And again, increase at the third time step and so on, okay? So until the outputs explode, okay? So because ReLU, it's very, the nature of ReLU is like that. So a non-saturating activation function does not prevent that, okay? So you can reduce this risk by using smaller learning rate, okay? But you can also simply use a saturating activation function. For example, like hyperbolic tangent. That is why, okay, a lot of people, when it comes to RNN, a lot of people prefer hypertangent, okay? Because hypertangent, when you increase it, hypertangent value is going to increase not that much. It's not going to be like ReLU, okay? Because the increase is linear. It's always linear. But the increase for the hypertangent is not linear. It's going to, because when it becomes saturated, the increase is very, very limited. Okay, so there's a certain reason why hypertangent is preferred in RNN. Okay, so in much of the same way, the gradient themselves can explode. If you notice the training is unstable, you may want to monitor the size of the gradient. For example, using like a TensorBoard. We talk about how you can use TensorBoard to monitor the training, but we didn't spend a lot of time on that. Okay, but it is a very useful tool. Okay, visualization tool. Okay, and you can use gradient clipping. We talk about gradient clipping, right? Okay, the same idea apply to RNN. Okay. Moreover, batch normalization cannot be used as efficiently with RNN as with deep feed-forward neural network, okay? Because you cannot use it between time steps, only between recurrent layers. Because batch normalization is used between layers, right? But in the RNN, remember, okay, the training is has 2 dimensions. One dimension is in between layers. The second dimension is in between different time steps, right? And a lot of time, the RNN cannot converge well. It's not because it has too many layers. Normally, okay, you don't see RNN to have too many layers anyway. It's not like CNN. CNN normally is very deep, but RNN is not that deep normally. Okay, but a lot of time, what you are going to see is RNN gets to process very long sequences. Okay, in other words, the unrolled through time will go very far. Okay, so on the other, in other words, this batch normalization, because it doesn't work well. It doesn't work for the time dimension, time stamp dimension. So that's why I say, it doesn't. It's not as efficient as deep forward neural network. Okay, so to be more precise, it is technically possible to add a BN layer to memory cell. Okay, so that it will be applied at each time step. Okay. However, the same BN layer will be used at each time step with the same parameters, regardless of the actual scale and offset of the input and the hidden state. Okay, in practice, this does not yield good results. Okay, So as was demonstrated by this guy, okay, in another paper, okay. So the author found that Bn was slightly beneficial only when it was applied to the input, not to the hidden state, okay. In other words, it was slightly better than nothing when applied between recurrent layers. Okay, so it's really not that useful, okay. But not within recurrent layers, okay. So in Keras, this can be done simply by adding a batch normalization layer before each recurrent layer, but don't expect too much from that, okay. So, well, we know, okay, Bn is so important, especially in CNN, okay. It's to a point that we don't even need to draw that in the architecture, because every time you see a convolutional layer, I mean, by default there will be a batch normalization. But unfortunately, batch normalization is not that useful for RNN, okay, as has been shown by some research, okay. So what do we do? Okay, we can, we have another form of normalization, okay. It normally works better with RNN, which is called layer normalization, okay. So this idea was introduced by this Jimmy Leiba. This is I think this is a guy from China, okay, because the Jimmy is his English name, I guess. So in a 2016 paper, so it's very similar to batch normalization, but instead of normalizing across batch dimension, it normalizes across the feature dimension, okay. So one advantage is that it can compute the required statistics on the fly and at each time step independently for each instance, okay. So this also means that it behaves the same way during training and the testing, okay. And so remember, in the batch normalization, we need to do something different. I mean, during training and during testing, right? But in layer normalization, we don't need that, okay, because it behaves the same way, okay, and it does not need to use exponential moving average to estimate the feature statistics across all instances in the training set, okay, which is like what we need to do. I mean, for batch normalization, okay. So like batch normalization, layer normalization learns a scale and offset parameter for each input. In RNA, it is typically used right after the linear combination of the input and the hidden state. So we'll see an example. Okay, so we're running out of time. So let's stop here. Okay, we are going to next hopefully in the next class. Okay, I can what which slide is this one? This is slide huh? Oh yeah, 46. So we have like about less than 24 slides left. I think we will finish this chapter before end of next lecture and then move on to the autoencoder chapter. Okay, so do I have autoencoder handout on the in the E class already? Not yet. Okay, so I will put it on the E class. Okay, today. Okay, just want you to know. Okay, based on our progress, I hope I will have a little bit more than 2 lectures for autoencoder. Hopefully, I can finish autoencoder chapter. Okay. So, any question today? Yes. Sorry.
According to the syllabus I said in the start of the semester,
Uh-huh.
the grading is for the 3 small project and final project.
Yes, yes, yes.
I haven't seen the final exam.
No. There's a final exam. Yes.
So the grading is not in the syllabus.
Oh, really? Oh, yeah. I made a mistake. Okay, but we will have final exam. Okay, I'll put it back. Okay, let me explain what happens. Okay, because at the beginning of this semester, okay, we are not. It's not possible for us to have exam because of COVID-19. Okay, because we have class size in terms of class size, our class size, we are not supposed to have face-to-face class at the beginning of the semester. Okay, so I removed the final exam from the syllabus. Okay, but okay, since now we already we don't have this restriction now, right? We have like a face-to-face lecture now. Okay, of course, in the real exam, okay, I will still borrow at least one additional classroom, okay, so that you guys can sit apart from each other when the exam is held, okay. So supposedly you should not worry about COVID-19 issue, okay. Of course, if situation change before the final exam, then I will cancel it. Okay, if the COVID-19 protocol, say we have Omicron, in Taiwan, then we cannot have exam, then I'm going to change. I'm going to stick with the regulation. But at this moment, because we already have face-to-face class for 2 months already, right? Yeah. So I suppose, the rest of the months will be also like that. So, yeah, and thank you for remind me that. I will change the syllabus. Okay, it's not like I try to cheat you guys. By introducing the final exam. Okay, it's just because of the regulation at the beginning of the semester, I cannot write we have exam. Okay, in the class. Okay, so just want you to be aware of that. Okay. So having said that, okay, let me repeat. Okay, we will have final exam. Okay, and the final exam percentage will be. Let me check. Okay, I will stick with what I used to do. Okay, for this class, I believe it's about 20 to 25%. Okay, but let me check. Okay, and once I will have TA to announce that, just to make sure everybody is aware of that. Okay. So yeah, thank you for reminding. Okay, any other question? If no question, that's it for today. Okay, thank you very much.